guys, hi everyone, welcome to Easy Tech. In this lecture, I will discuss the types of DC generators. Types of DC generators. There are two types of DC generators. One is self-excited DC generator, self-excited DC generator, and second one is separately excited DC generator. In this self-excited DC generator, we have a DC shunt generator, DC series generator, and third one is DC compound generator. In this DC compound generator, based on the connections, we can divide it as long shunt and short shunt connection. And based on the compounding levels, we can divide as cumulative compound and differential compound DC generator. So the first one is separately excited DC generator. We have two windings. One is armature winding and another one is field winding. The armature is represented with circle with two brushes, that armature winding, which has two terminals A and A, and the field winding terminals are represented with F and FF. A is the starting terminal of the armature winding, the A is the finishing terminal of the armature, and F is the starting terminal of the field winding, and FF is the finishing end of the field winding. Based on the connections between these two, we can say that shunt, series, and compound levels. In the compound, we require another connection also. Separately excited means, as the name itself, it is a separately excited. The field winding is separately excited with an external source. The field winding is excited with separately an external source, then it is called as a separately excited DC generator. The armature is driven with the external device. That device is called the prime mover. So prime mover is an external device which is used to drive the armature. So the armature terminals are represented with A and AA. The field winding is represented with F and FF. When the field winding is excited with an external source, it will produce a magnetic field with drawing a current of IF. So the field winding resistance will be RF. We can write the equation V is equal to IF into RF by applying the KVL to this loop, minus V plus IF RF is equal to 0. Then the field current IF is equal to V divided by RF. With this rotation, the generated EMF will be induced in an armature conductors. Armature winding consists of a resistance RA and the load resistance will be RL. The current which is delivered from the armature is called IA. And the current which is flowing through load is called load current. So where IA is the armature current, IA is the armature current, IL is called the load current, and IF is called the field current, and RF is the field resistance. RF is the field resistance. The voltage which is appeared across the load terminal is called the VL or VT. So where VT is called the terminal voltage, terminal voltage. So if you apply KVL to this loop, then we will get one equation. So I am drawing separately. See, in an armature I have a EG is a generated EMF, and the armature resistance is RA, and the terminal voltage is VT. So always the current flows from higher potential to lower potential. Higher potential is represented with plus and the lower potential is represented with minus. So apply KVL to this loop. Current enters into the positive terminal can be treated as positive. You can follow any notation for easy understanding. I am telling like this: current enters into the positive terminal S can be treated as positive IARA. Here also current enters into the positive terminal means plus VT. So minus EG is equal to 0, where EG is equal to VT plus IA into RA if a small brush contact drop is there, where BCD is called brush contact drop. BCD is called the brush contact drop. So our generated EMF should meet the terminal voltage plus some drop IARA and the brush contact drop. The field winding current IF is independent on terminal voltage. So in this separately excited machine, the field current is independent of terminal voltage. You can remember, it is very important. And coming to the second classification, self-excited DC generator. Self-excited DC generator means based on the connections between the field winding and armature winding, we can tell the shunt, series and compound. The generator field winding is excited by its own, that's why it is called as a self-excited. So here the armature terminals are represented with A and AA, and the field winding is connected in shunt with the armature. The field terminals are F and FF. F and A will be short circuited and FF and AA will be short circuited and take a terminal out, and you can connect one external load. The voltage which is appeared across the terminal or load is terminal voltage. The generated EMF is EG and the internal resistance will be RA. The current delivered from the armature is IA. This current is divided into two parallel paths. One is IL and another one is ISH. Again, you can apply the KVL to this loop, and always the current goes from higher potential to lower potential. This is EG and the armature resistance is RA. Always the current flows from higher potential to lower potential. the terminal voltage will be Vt. So here I am connecting a load. So now you can apply KVL to this loop. Minus Eg plus IaRa plus Vt is equal to 0, and Eg is equal to Vt plus IaRa plus BCD, where BCD called the brush contact drop. So here you can apply KCL at this node. So KCL at this node, Ia is equal to, the armature current is equal to IL plus ISH. Previously, the Ia current is equal to IL. Previously, the Ia current is equal to IL. That means armature current is equal to load current in separately excited DC generator. But in a self-excited DC generator, Ia is equal to IL plus ISH. If you close the switch, the same terminal voltage will be appeared. The same terminal voltage will be appeared at this node. The Vt will be appeared. The voltage is Vt. So same terminal voltage is appeared across RSH. Now the field winding resistance is RSH. RSH is called the winding shunt field winding resistance. Shunt field winding resistance. If you have a doubt, you can apply KVL to this loop also. What is the meaning of this one? Apply KVL. What is the current now? The current which is flowing through this field winding is called the shunt current. So this is the current flowing through shunt field winding. Current flowing through field winding is called shunt current in this case, and ISH is equal to Vt divided by RSH. If you have a doubt, so you can apply KVL to this loop. Yes, this is a Vt, and the current is flowing here ISH, and this one is RSH. Always the current flows from higher potential to lower potential, and you can apply KVL to in this loop. So minus ISH into RSH plus Vt is equal to 0. Then ISH RSH is equal to Vt. Then I got the answer, ISH is equal to Vt by RSH. So you can apply if you have a doubt. When a loop is available, you can apply KVL. And if you have a doubt when a node is available, you can apply KCL. In this case, IA is equal to IL plus ISH. The armature current is to meet the load current and shunt current. Now, the second connection is called DC series generator. DC series generator. The first one is DC shunt. The first one is DC shunt generator. This type of connection is called the DC shunt generator. It is under the category of self-excited DC generator. The second one is DC series generator. Means both armature winding and field are connected in series. Again same thing, armature winding is dependent with A and A, and the field winding is connected like this, and let us say this is F and FF. The armature is driven with an external prime mover. In the previous case also same thing, and it is connected to load. So the internal generated EMF is Eg. The internal EMF is Eg, and armature winding resistance will be Ra, and the field winding resistance will be Rse. The current which is delivered from the armature is Ia, and the current which is flowing through the series field winding is ISC. The current which is flowing through the load is IL. We have a one relationship IA is equal to ISC is equal to IL. IA is equal to ISC is equal to IL. And if you apply the KVL to this loop, the terminal voltage is VT. So now I am drawing the circuit separately. EG and the armature resistance is RA and series field winding resistance is RSC and the terminal voltage is VT and upper terminal is positive and lower terminal is negative. Current delivered from the armature is IA. So this is plus and minus. This is also plus and minus. So minus EG plus IARA plus IA into RSC plus VT is equal to 0. EG is equal to VT plus IA into RA plus RSC plus brush contact drop. In this equation, I am not representing the brush contact drop, but it's a very small drop, 2 volts. Okay, your brush contact drop is also subtracted. So EG equal to VT plus IA into RA plus RSC plus BCD. In series connection, IA is equal to ISC is equal to IL. So here the important question is why shunt field turns are more. Shunt field turns are more when compared to series field turns. So if you observe the shunt field winding is like this, it has more number of turns. But if you go for the series field winding of DC generator, it carries only few turns. Why? Because the shunt current is equal to VT divided by RSH. The RSH value is also high and the V2 value is also high. So 230, maybe it is 300 or approximately 230 to 300, it will be vary. So then if you take it 230 volts, 230 ohms, then I have a 1 ampere current in. I have a 1 ampere current. So this is IA and this one is IL. But coming to the DC series generator, it carries a load current. And generally the load current is in the range of 20 amperes. The current will be very, very large. The current will be very, very large. For a lower currents, the resistance value is more. If you observe the shunt field winding resistance is more. And why? Because suppose I have a 10 rupees in my pocket, 10 rupees. If 1 rupee is lost, then 9 rupees are utilized. In 10 rupees, if 9 rupees is lost, only I have 1 rupee. So which one is the best? My dear friends, tell me. So the case 1 is best and case 2 is worst. And most of the current is passes through the load terminals only. Only a part of the current is divided and current flows through field winding, which will produce as a required flux. So in order to get the more resistance, R is equal to rho L by A. The length should be increased and the area should be decreased, then only the resistance will be more. That's why the length of the field winding is more and cross sectional area of the conductor cross sectional area of conductor, cross sectional area of conductor is less. Coming to here, the resistance, if the same resistance is kept in series with the armature, the Ia square Ra value, the Ia square Rf value should be very high in this case. But it is, if the losses are more, then heat is also more, then the winding will be damages. Okay, same concept I am using. I require 10,000 watts at the load. Suppose 1000 watts. So 1000 watts at the load. But if the more loss will be occurred in a field winding, so let us assume it is 900 watts is the loss. Only 100 watts is the utilization. So utilization purpose. So this is not at all good. That's why we are designing a resistance with lower value. That RSC value should be very low. Should be very low. If RSC value is low, then what will happen? Ia square RSC value is also low. Then losses is low, heat is also low. In order to design the lower value of resistance, R is directly proportional to length per area. The length of the turns will be decreased and the cross-sectional area of the conductor is increased. So length will be decreased and cross-sectional area of conductor is increased. That's why series field turns are less, shunt field turns are more. So this is a very important question. And the third one is DC compound generator. DC compound generator. So still now we are discussing about the armature winding and shunt field winding or series field winding. Now in a DC compound generator, we have three windings. One is series field winding. And another one is shunt field winding. And third one is armature winding. So based on the connections between these three, we can divide it as long shunt and short shunt. Long shunt and short shunt. If you go for the long shunt connection, so this is our armature. So armature has two terminals and the field winding is connected in parallel. This is shunt field winding. And one more winding is also there, that is series field winding is connected in series with the armature. Series field winding is connected in series with the armature. Series field winding is connected in series with the armature. Then this type of connection is called long shunt connection. This type of connection is called the long shunt connection. So the current delivered from the armature is Ia and the current flowing through the series field winding is Isc, and the shunt field winding resistance is Rsh and series field winding resistance is Rsc. And this current is divided into two currents. One is load current and shunt current. If you apply KCL at this point, Ia is equal to IL plus ISH. Here Ia is equal to Isc. This is very important. And Ia is equal to ISC. And always the current flows from higher potential to lower potential. The terminal voltage is VT, and the potential at this point, potential between these 2 points is also VT. The voltage which is appeared across the shunt field winding is also VT. ISH is equal to VT divided by RSH. The internal induced EMF is EG, and armature resistance is RA. Now you can apply to the KVL to the last loop. So this is EG and RA and RSC. The terminal voltage is VT. The voltage which is applied across the load is VT. So always the current flows from higher potential to lower potential. Here also higher potential to lower potential. So apply KVL to this loop. Minus EG plus IARA plus IARSC plus, because the current enters into the positive terminal, plus VT is equal to 0. Now EG is equal to VT plus IA into RA plus RSC plus brush contact drop. Okay, this is about the long shunt connection. IA is equal to IL plus ISH, where ISH is equal to VT divided by RSH. And the second connection is a short shunt connection. In this short shunt connection, we are connecting a series field winding in series with the load. So the terminal voltage is VT, and the shunt field winding is connected in parallel with the armature. So this is plus and minus. Always the current is delivered from armature in generator. So IA is equal to IL plus ISH. IA is equal to IL plus ISH if you observe, and this consists of the current, series current. So IL is equal to IS. You can remember this one. So again you can apply the KVL to this loop. Minus EG plus IARA plus IL into RSC. IL into RSC. This is plus and minus. Plus VT is equal to 0. So EG is equal to VT plus IARA plus IL into RSC. Plus brush contact drop. BC is also there. But what is the potential at this point? The potential at this point is not VT. You should calculate that. So this is armature. Okay. So the voltage you can assume that Vx, because the voltage which is appeared across the shunt field winding is also Vx. Find out the Vx value. So this is a series field winding RSC, and this one is load. The terminal voltage is VT. The current is flowing in this direction. Okay, so this is plus and minus. So Vx minus Vx plus IL into RSC, the current which is flowing through load is a load current, plus VT is equal to 0. Now Vx is equal to VT plus IL into RSC. If we know the node potential SVx and Vx in terms of terminal voltage and the load current, can I calculate the shunt current or not? Yes or no? So shunt current is equal to Vx divided by RSH. Vx is VT plus IL into RSC divided by RSH. This is about the shunt current. So if you have a doubt, apply KVL. So it's very simple, and IA is equal to, if you apply the KCL at this point, IL plus ISH. So what is meant by cumulative compound machine? Cumulative compound DC generator. Cumulative compound means I am drawing one pole here. So differential compound. So here I also am drawing. The winding is wound like this. These are called the shunt field turns, and series field turns are also wound like this. If the sense of winding is same, if the current is passes in this direction, here also current is passing in the same direction. If you apply the right hand grip rule, the flux produced by the shunt field winding is downwards, and the flux produced by the series field winding is also downwards. This is phi sh and this one is phi sc. The net flux will be phi sh plus phi sc. Then this type of connection is called cumulative connection. Here also I am on the winding. So this is the sense of winding. Generally shunt field winding turns are more, but here I am drawing only less only. So here the current is passed like this. Here the current is passed like this. Then the current is leaves the series field winding, but the current enters like this left side, and this one is right side. So the flux will be produced by the shunt field winding will be downward. If you apply the right hand grip rule, the flux produced by the series field winding is upward. So always the shunt field flux is greater than series field flux, but the net flux will be phi sh minus phi sc. So that's why this type of connection is called the differential compound DC generator. This type of connection is called the differential compound DC generator. In this lecture, I am teaching different types of DC generators. Self-excited DC generator, separately excited DC generator. The field winding is separately excited by an external source. That's why it is called separately excited DC generator. So in a self-excited DC generator, we have a DC shunt generator, and next one is DC series generator, and after the DC compound generator. In this compound generator, so we have a long shunt and short shunt connections. After that, the long shunt and short shunt, cumulative compound generator and differential compound generators. So I think you understand the students and friends. So thank you.